we're going to be looking into solving problems involving angles. And an important thing to note is that anytime you solve a problem where you have a surface that's angled, right, is that the normal force is always going to be at a 90-degree angle from that surface. And likewise, the frictional force, if there is one, will always occur perpendicular to the normal force and parallel to the plane. This is really important because it changes how you might normally set an axis. Under normal circumstances, we set it so that the y is in the vertical plane and the x is along the horizontal plane. But when you're dealing with an angle away from the surface, you want to set your x and your y axis so that you're not resolving for every single vector. And so in this circumstance, we would want to set our x and our y axis so that the x-axis is parallel to the plane and the y-axis is parallel to the normal force. What happens then is that your force of gravity is always going to be at some angle from your axis, and we don't know what that angle is. So let's take a look at solving a problem. Here we have Benny the skier. Benny has been keeping a secret from you that he knows how to ski very well this whole time. In this situation, he is just taking off, so there's a few things that we can assume. One of those things is since he's just taking off, he's taking off from rest. Another thing that we're given is that the coefficient of kinetic friction or sliding friction between the surface and Benny's skis is 0.1. So we want to know what his acceleration is. And once we have that acceleration, we want to be able to calculate his velocity after he's been going down this hill at 4 seconds. So taking a look at the free body diagram of this situation, you've got yourself a normal force and a frictional force, which are, of course, perpendicular to one another. And then we've got ourselves a gravitational force downward. So I want to set my axis, and I want to set it to give me the least amount of calculation as possible. So I'm going to be setting my axis along the x plane or parallel to the angle. Remember that that angle, or that angled surface, was a 30-degree incline. And that's going to matter in a moment when we take a look at how we resolve for the angle here, which is unknown. So remember that in any right triangle and to the horizon, all gravity forms a right angle. So in that situation, you have a 30-degree triangle, so the angle between gravity and the axis is going to be what is remaining in this situation, or 60 degree. And so that's really convenient. But the other thing that you're going to note is that that 30 degree is also the 30 degree between the gravity and the y-axis. So this gives you two options. You can resolve for the x and y component of the force, where this is mgy and this is mgx, or you can resolve for the x and y components on this side, where this is mgy and this is mgx. So you might ask, why does that matter? And it matters because if you're using this angle of 60 degree, this angle of 60 degree is cosine to the x component. But if you're using this angle right here, 30 degree, this angle of 30 degree is sine to the x. So it actually makes a great deal of difference which angle you're resolving for. So in red, if we take a look at resolving the components on this side, mgy is going to equal mg cosine of 30, and mgx is going to be equal to mg sine of 30. And this is opposite to our normal situation where the y component is always sine and the x component is always cosine. And there's nothing wrong with that. It's just that this time when we take a look at what that angle is not to the positive x-axis. That angle is between gravity and the y-axis, and that's what changes those around. If you're uncomfortable with this, you can continue to use the angle that's to the positive x-axis, and in that situation, mgx would be equal to mg cosine of 60, and mgy would be equal to mg sine of 60. And looking at these values, you know that this equation and this equation would give you the exact same amounts. So you're going to decide to do whatever you're most comfortable with. But we've broken our free body diagram down. We have our components, so let's go ahead and let's solve. Solving for the net force in the y direction, we have ourselves the normal force minus the y component of gravity. And I'm going to go ahead and use red. So the y component of gravity is going to be the mg cosine of 30. And in this situation where Benny's sliding down a hill, he is only moving along the x-axis, so that's going to be equal to 0. And the sum of the forces in the x direction is going to be equal to the frictional force in the opposite direction, and your positive force is coming from the x component of gravity. So we've got mg sine of 30 minus the force of friction, and that will equal the mass times the acceleration. And that's our declaration statement, that the acceleration in the y direction is 0, or uniform motion, and the acceleration in the x direction is going to be equal to mass times acceleration. So here we can take a look at a few things. First thing that we know is that the force of friction is due to kinetic friction, so that's going to be equal to the coefficient of kinetic friction times the normal force. And we know that the normal force from our y components is going to be equal to mg cosine of theta. So we're going to go ahead and we're going to plug that in, and we're going to say that the force of friction is going to be equal to the coefficient of kinetic friction times mg cosine of 30. So now I'm going to take that and I'm going to plug it into this equation here, and I get that mg sine of 30 minus coefficient of friction mg cosine of 30 is going to be equal to mass times acceleration. And you notice that the only numerical value that we're given this whole time is the angle of 30 degrees. Everything else is in units. But I can eliminate units because you see I have mass on this side and I have mass as a component of everything on this side. So I'm going to get rid of my masses. And I get that g sine 30 minus g cosine 30 is going to equal our acceleration. Now, g is a variable, but it's a variable with a known quantity, so I can solve for my gravity in this situation. I can plug it in, and I can end up with a numerical value. And when I take my variable, I should get that g sine 30 minus the coefficient. Sorry, I left out my coefficient. I just now realized that I left out my coefficient here. So that should be mk g sine 30. I was thinking that something was off there, but I'm going to get 9.8 sine 30 minus 0.1 times 9.8 cosine 30, and that will equal a. So I crunch those numbers numerically, and I get that acceleration is going to be, where'd my little calculator? Oh. So I take my 9.8 times sine of 30, and I subtract 0.1 times 9.8 times the cosine of 30, and I end up getting that acceleration equals 4.05 meters per second squared. Now, if I had left my g in the equation and I'd had that g sine 30 minus 0.1 g cosine 30, I would have ended up getting 0.41 g's. Alright, 0.41 g's should end up giving me the exact same variable. And it does. So, now that I know what the acceleration is, I can figure out what the acceleration is after 4 seconds. And I can do that because I know that the velocity is going to be equal to the initial velocity plus acceleration times time. I resolved my acceleration right here. So I get two significant figures because that was my limiting amount. I get that the velocity is going to equal 0, our starting velocity, plus 0.41 times 4 seconds, and that's going to equal about 16 meters per second when I round it to two significant figures. So you can see that it's really kind of neat because here you get that gravity is a major player in your x component, and if you have a frictionless surface, gravity becomes your only x component in a free body diagram. Otherwise, gravity is your only component that's combating friction. So an object is either going to be stationary if its static friction is large enough, or it's going to be sliding downhill because the force of gravity in the x direction is larger than the force of friction that the two surfaces can provide. So I do want to take a pause, and I want to make sure to take a look at solving for components, and we're going to take a look at situations that are entirely non-numerical and what some of the benefits and what some of the drawbacks are from choosing various things. So the first thing is we're going to consider a spherical Benny, and this spherical Benny isn't rolling down the hill, the spherical Benny is sliding down the hill, because we're only looking at translational motion, which means we're only looking at what the result of all of his motion is causing him to do. In that case, our free Benny diagram is going to be gravity, normal force, and friction. And this should look very similar to everything that we've done so far. When we set our axis up, so that the x-axis is parallel to the surface, and we know that we've got components that we have to deal with. And so I asked that question before, which angle do you want to use? Right? And some people might be uncomfortable with using the angle on this side because it changes what the y and the x component are from before our vector addition. Now, if you don't know your angle is unknown, then using similar triangles, we know that that's 30 degrees, so this is going to be, that's theta degrees, so this is going to be, on a right triangle, it's going to be 90 minus theta, and this over here is going to be theta. Alright, and that's because that's a 90-degree angle. And that means that you've got a similar triangle on this side. Right? Now here's where I might encourage you to choose this angle from the similar triangles to resolve for your gravitational components. And it's because if your angle is unknown and you're solving for your x and your y component, there and there, Instead of having to constantly plug in an unknown angle 90 minus theta when you resolve, if you are willing to swap it because you know that mgy is going to be equal to mg cosine theta and mgx is going to be equal to mg sine theta, if you're willing to make that switch and visually acknowledge the y-axis is the angle between the y-axis and gravity, and that's going to be a cosine, and this is going to be a sine, then this is going to end up being a simpler problem-solving method as long as you're willing to take that leap.